Hello and welcome. My name is Alan, and today we'll be doing more ideas and opinions of Albert Einstein. We're going to be reading two pieces. First piece is fairly long. Second piece is a little quick one. First piece is called "The Mechanics of Newton and Their Influence on the Development of Theoretical Physics." On the occasion of the 200th anniversary of Newton's death, published in volume 15 of the German periodical Die Naturwissenschaften, 1927. That's what the blurb reads. It is just 200 years ago that Newton closed his eyes. We feel impelled at such a moment to remember his brilliant genius, who determined the course of Western thought, research, and practice like no one else before or since. Not only was he brilliant as an inventor of certain key methods, but he also had a unique command of the empirical material available in his day. And he was marvelously inventive as regards detailed mathematical and physical methods of proof. For all those reasons, he deserves our deepest reverence. The figure of Newton has, however, an even greater importance than his genius warrants, because destiny placed him at a turning point in the history of the human intellect. To see this vividly, we have to realize that before Newton, there existed no self-contained system of physical causality which was somehow capable of representing any of the deeper features of the empirical world. No doubt the great materialists of ancient Greece had insisted that all material events should be traced back to a strictly regular series of atomic movements, without admitting any living creature's will as an independent cause. And no doubt Descartes had in his own way taken up this quest again, but it remained a bold ambition, the problematic idea of a school of philosophers. Actual results of a kind to support the belief of the existence of a complete chain of physical causation hardly existed before Newton. Newton's object was to answer the question, is there any simple rule by which one can calculate the movements of the heavenly bodies in our planetary system completely, when the state of motion of all these bodies at one moment is known? Kepler's empirical laws of planetary movement, deduced from Tycho Brahe's observations, confronted him and demanded explanation. But these laws gave, it is true, a complete answer to the question of how the planets move round the sun, the elliptical shape of the orbit, the sweeping of equal areas by the radii in equal times, the relation between the major axes and the periods of revolution. but these rules do not satisfy the demand for casual explanation. They are three logically independent rules, revealing no interconnection with each other. The third law cannot simply be transferred quantitatively to other central bodies than the sun. There is, e.g., no relation between the period of revolution of a planet around the sun and that of the moon around its planet. The most important point, however, is this. These laws are concerned with the movement as a whole and not with the question how the state of motion of a system gives rise to that which immediately follows it in time. They are, as we should say now, integral and not differential laws. The differential law is the only form which completely satisfies the modern physicist's demand for causality. The clear conception of the differential law is one of Newton's greatest intellectual achievements. It is not merely this conception that was needed, but also a mathematical formalism which existed in a rudimentary way but needed to acquire a systemic form. Newton found this also in the differential and the integral calculus. We need not consider the question here whether Leibniz hit upon the same mathematical methods independently of Newton or not. In any case, it was absolutely necessary for Newton to perfect them, since they alone could provide him with the means of expressing his ideas. Galileo had already made a significant beginning toward a knowledge of the law of motion. He discovered the law of inertia and the law of bodies falling freely in a gravitational field of the Earth, namely that a mass, more accurately a mass point, which is unaffected by other masses, moves uniformly and in a straight line. The vertical speed of a free body in the gravitational field increases uniformly with time. It may seem to us today to be but a short step from Galileo's discoveries to Newton's law of motion, but it should be observed that both the above statements are so formulated as to refer to the motion as a whole, while Newton's law of motion provides an answer to the question. How does the state of motion of a mass point change in an infinitely short time under the influence of an external force? It was only by considering what takes place during an infinitely short time, differential law, that Newton reached a formulation which applies to all motion whatsoever. He took the concept of force from the science of statics, which had already reached a high stage of development. He was only able to connect force and acceleration by introducing the new concept of mass, which was supported, strange to say, by an illusory definition. We are so accustomed today to form concepts corresponding to differential quotients that we can now hardly grasp any longer what a remarkable power of abstraction it needed to obtain the general differential law by double limiting process, in the course of which the concept of mass had in addition to being invented. But a causal concept of motion was still far from being achieved, for the motion was only determined by the equation of motion in cases where the force was given. Inspired, no doubt, by the laws of planetary motions, Newton conceived the idea that the force operating on a mass was determined by the position of all masses situated at a sufficiently small distance from the mass in question. It was not till this connection was established that a completely causal concept of motion was achieved. How Newton, starting from Kepler's laws of planetary motion, performed this task for gravitation, and so discovered that the moving forces acting on the stars and gravity were the same nature, is well known. It is the combination. Law of motion plus law of attraction. It is the combination which constitutes the marvelous edifice of thought, which makes it possible to calculate the past and future states of a system from the state obtaining at one particular moment, insofar as the events take place under the influence of the forces of gravity alone. The logical completeness of Newton's conceptual system lay in this, that the only causes of acceleration of the masses of a system are these masses themselves. On the basis of the foundation here briefly sketched, Newton succeeded in explaining the motions of the planets, moons, and comets down to the smallest details, as well as the tides and the precessional movement of the Earth. A deductive achievement of unique magnificence. The discovery that the cause of the motions of the heavenly bodies is identical to the gravity with which we are so familiar from everyday life must have been particularly impressive. But the importance of Newton's achievement was not confined to the fact that it created a workable and logically satisfactory basis for the actual science of mechanics. Up to the end of the 19th century, it formed the program of every worker in the field of theoretical physics. All physical events were to be traced back to the masses subject to Newton's laws of motion. The law of force simply had to be extended and adapted to the type of event under consideration. Newton himself tried to apply this program to optics, assuming light to consist of inert corpuscles. Even the wave theory of light made use of Newton's law of motion after it had been applied to continuously distributed masses. Newton's equations of motion were the sole basis in the kinetic theory of heat, which not only prepared people's minds for the discovery of the laws of conservation of energy, but also led to the theory of gases, which had been confirmed down to the last detail, and a more profound view of the nature of the second law of thermodynamics. The development of electricity and magnetism had proceeded up to modern times along Newtonian lines, electrical and magnetic substance, forces acting at a distance. Even the revolution in electrodynamics and optics brought about by Faraday and Maxwell, which formed the first great fundamental advance in theoretical physics since Newton, took place entirely under the aegis of Newton's ideas. Maxwell, Boltzmann, and Lord Kelvin never wearied of tracing the electromagnetic fields and their dynamic interactions back to the mechanical action of hypothetical continuously distributed masses. As a result, however, of the lack of success, or at any rate of any marked success of those efforts, a gradual shift in our fundamental notions had taken place since the end of the 19th century. Theoretical physics has outgrown the Newtonian frame, which gave stability and intellectual guidance in science for nearly 200 years. Newton's fundamental principles were so satisfactory from the logical point of view that the impetus to overhaul them could only spring from the demands of empirical fact. But before I go into this, I must emphasize that Newton himself was better aware of the weaknesses inherent in his intellectual edifice than the generations of learned scientists which followed him. This fact has always aroused my deep admiration, and I should like, therefore, to dwell on it for a moment. 1. Newton's endeavors to represent his system as necessarily conditioned by experience and to introduce the smallest possible number of concepts not directly referable to empirical objects is everywhere evident. In spite of this, he set up the concept of absolute space and absolute time. For this, he has often been criticized in recent years. But in this point, Newton is particularly consistent. He had realized that observable geometrical quantities, substances of material points from one another, and their course in time do not completely characterize motion in its physical aspects. He proved this in the famous experiment with the rotating vessel of water. Therefore, in addition to masses of temporally variable distances, there must be something else that determines motion. That something he takes to be relation to absolute space. He is aware that space must possess a kind of physical reality if his laws of motion are to have any meaning, a reality of the same sort as material points from their distances. The clear realization of this reveals both Newton's wisdom and also a weak side to his theory. For the logical structure of the latter would undoubtedly be more satisfactory without this shadow concept. In that case, only things whose relations to perception are perfectly clear, mass points, distances, would enter into the laws. 2. Forces acting directly and instantaneously at a distance, as introduced to represent the effects of gravity, are not in character with most of the processes familiar to us from everyday life. Newton meets this objection by pointing to the fact that his law of gravitational interaction is not supposed to be a final explanation, but a rule derived by induction from experience. 3. Newton's theory provided no explanation for the highly remarkable fact that the weight and the inertia of a body are determined by the same quantity, its mass. Newton himself was aware of the peculiarity of this fact. None of the 3 points can rank as a logical objection to the theory. In a sense, they merely represent unsatisfied desires of the scientific mind in a struggle for a complete and uniform conceptual grasp of natural phenomena. Newton's theory of motion, considered as a program for the whole of theoretical physics, received its first blow from Maxwell's theory of electricity. It became clear the electric and magnetic interactions between bodies were affected not by forces operating instantaneously at a distance, but by processes which are propagated through space at a finite speed. In addition to the mass point and its motion, there arose, according to Faraday's concept of a new kind of physical reality, namely the field. At first, people tried adhering to the point of view of mechanics to interpret the field as a mechanical state of motion or stress of a hypothetical medium, the ether, permeating space. But when this interpretation refused to work in spite of the most obstinate efforts, people gradually got used to the idea of regarding the electromagnetic field as the final irreducible constituent of physical reality. We have H. Hertz to thank for definitely freeing the concept of the field from all encumbrances derived from the conceptual theory of mechanics, and H. A. Lorentz for freeing it from a material substratum. According to the latter, the only thing left as substratum for the field was a physical empty space or ether, which even in the mechanics of Newton had not been destitute of all physical functions. By the time this point was reached, nobody any longer believed in immediate momentary action at a distance, not even in the sphere of gravitation, although no field theory of latter was clearly indicated owing to lack of sufficient factual knowledge. The development of the theory of the electromagnetic field, once Newton's hypothesis of forces acting at a distance had been abandoned, led also to the attempt to explain the Newtonian law of motion on electromagnetic lines, or to replace it by a more accurate one based on field theory. Even though these efforts did not meet with complete success, still the fundamental concepts of mechanics had ceased to be looked upon as fundamental constituents of the physical cosmos. The theory of Maxwell and Lorentz led inevitably to the special theory of relativity, which, since it abandoned the notion of absolute simultaneity, excluded the existence of forces acting at a distance. It followed from this theory that mass is not a constant quantity, but depends on, indeed, it is equivalent to, the energy content. It also showed that Newton's law of motion was only to be regarded as a limiting law valid for small velocities. In its place, it set up a new law of motion in which the speed of light in vacuo figures as the limiting velocity. The general theory of relativity formed the last step in the development of the program of the field theory. Quantitatively, it modified Newton's theory only slightly, but for that and the more profoundly qualitatively, inertia, gravitation, and metrical behavior of bodies and clocks were reduced to a single field quality. This field itself was again postulated as dependent on bodies, generalization of Newton's law of gravity, or rather the field of law corresponding to it as formulated by Poisson. Space and time were thereby divested not of their reality, but of their causal absoluteness, i.e., affecting but not affected, which Newton had been compelled to ascribe to them in order to formulate the laws then known. The generalized law of inertia takes over the function of Newton's law of motion. This short account is enough to show how the elements of Newtonian theory passed into the general theory of relativity, whereby the three defects above mentioned were overcome. It looks as if in the framework of the theory of general relativity, the law of motion could be deduced from the field law corresponding to the Newtonian law of force. Only when this goal has been completely reached will it be possible to talk about a pure field theory. In a more formal sense, also Newton's mechanics prepared the way for field theory. The application of Newton's mechanics to continuously distributed masses led inevitably to the discovery and application of partial differential equations, which in their turn first provided the language for the laws of the field theory. In the formal respect, Newton's conception of the differential law constitutes the first decisive step in the development which followed. The whole evolution of our ideas about the processes of nature with which we have been concerned so far might be regarded as an organic development of Newton's ideas. But while the process of perfecting the field theory was still in full swing, the facts of heat radiation, the spectra, radioactivity, etc., revealed a limitation in the applicability of this whole conceptual system, which today still seems to us virtually impossible to overcome, notwithstanding immense successes in many instances. Many physicists maintain, and there are weighty arguments in their favor, that in the face of these facts, not merely the differential law, but the law of causation itself, hitherto the ultimate basic postulate of all natural science, has collapsed. Even the possibility of a spatio-temporal construction, which can be unambiguously coordinated with physical events, is denied. That a mechanical system can have only discrete permanent energy values or states as experienced almost directly seems at first sight hardly deducible from a field theory which operates with differential equations. The de Broglie-Schrödinger method, which has in a certain sense the character of a field theory, does indeed deduce the existence of only discrete states in surprising agreement with the empirical facts. It does so on the basis of differential equations applying a kind of resonance argument, but it was to give up the localization of particles and strictly causal laws. Who would presume today to decide the question whether the law of causation and the differential law, these ultimate premises of the Newtonian view of nature, must definitely be abandoned? So yeah, Einstein talking about Newton and how he has affected physics, how his observation and laws are still applicable to the sciences even in Einstein's time, 200 years later. Next piece is called On Scientific Truth. Blurb reads, Answers to Questions of a Japanese Scholar, published in Gelaginteliches 1929, which appeared in a limited edition on the occasion of Einstein's 50th birthday. 1. It is difficult even to attach a precise meaning to the term scientific truth. Thus, the meaning of the word truth varies according to whether we deal with a fact of experience, a mathematical proposition, or a scientific theory. Religious truth conveys nothing clear to me at all. 2. Scientific research can reduce superstition by encouraging people to think and view things in terms of cause and effect. Certain it is that a conviction akin to religious feeling of the rationality or intelligibility of the world lies behind all scientific work of a higher order. 3. This firm belief, a belief bound up with deep feeling in a superior mind that reveals itself in the world of experience, represents my conception of God. In opinion, or in common parlance, this may be described as pantheistic. Spinoza. 4. Denominational traditions I can only consider historically and psychologically. They have no other significance for me. So yeah, just a list of answers. I don't know what the questions were that he was answering, but some answers regardless by Einstein. But yeah, as always, educate thyself, think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite their sources. I'll see you all in the next video. Until then, later.